Hi everybody, going to be looking at the types of processors today. So this is a knowledge sprint, so let's get on with it. 3, 2, 1, let's go. Okay, so we're going to look at CISC and RISC today. So the difference between CISC and RISC is that CISC is complex instruction set computing, whereas RISC is reduced instruction. So in other words, we've got two alternative ways of processing, one where we've got kind of a very complex structure to it, one where it's very simplified. And there are advantages and disadvantages to each of these two situations. If we compare them here, we can sort of see how the hardware is different. So that with a complex, we've got the more difficult hardware to actually create. It's complicated in its design, but what it can do is it can carry out sort of more complex activities compared with our simpler hardware, where we've got a simpler processor design, and therefore we have that comparison in the speed of which it can run as well. Again, because of the differences in the structures, our CISC therefore requires less program code. In other words, one instruction will do much more of a complex activities, whereas with our RISC, one instruction will only do one thing, and therefore you need much more lines of code to be able to carry out an instruction as you move forwards. Okay, we can also think about the costs in this. So with CISC, it's more expensive to produce, but also requires more power because of the complexity going on, more cooling is required, etc. Whereas with a RISC processor, cheaper to produce, lower power usage, in other words, perfect for our mobile situations. So many laptops, phones, etc. will use a RISC processor, whereas your desktop computers or sort of computers requiring really quite intensive processing capability needs will therefore be CISC. Okay, so obviously with a processor, we want to think about improving performance of a processor. So the first thing we can do is have a co-processor with it. In other words, what we want to do is to have two processors working on an activity at once. A classic example of this would be something like a GPU, where it would be processing any graphics that are going on. So in other words, you have your main processor with however many cores you've got in there, but then you also have a GPU alongside it, which is then carrying out specific tasks. So in the case of a graphical processor, it's most likely to be actual graphics related things. So it might be portraying images on a screen, video on a screen, etc. Whereas the actual main code will be carrying out the rest of it. So you can sort of see from this diagram how it actually may only help in a sort of small percentage of your code, but if you think that particular percentage might be incredibly processor intensive, and therefore the GPU can carry it out much quicker than a CPU would. And also if you think it's not getting in the way of the tasks as well of the original CPU. We can also have multi-core processors. So in other words, we have more than one core within a single processor. They share resources. So in this example here, they've only got their own level 1 cache, but they're sharing a level 2 cache. What you can also have is a shared level 3 cache as well if you need it. So there's a flexibility to this. This is just a simple basic architecture for it to sort of show how they would share resources and work alongside each other. With a multi-core processor, one of the big advantages you get here is this concept of threads. In other words, these short single sequence of instructions, the scheduler therefore chooses which instruction to be carrying out, and therefore we get a very strong sense of activities happening at the same time. In reality, they're not happening actually at the same time. Time slicing is therefore allowing sort of very short milliseconds period of time for one process to be actioned, and then it will pause that, store its state, and then move on to the next thread. And then by looping through multiple jobs all at once, to us as the user, it feels like they're all happening at exactly the same time. And like I said, in reality, they're not. But when we think about the timings of this, we're talking about like billions of instructions per second. So to the human, it's completely imperceptible. Whereas obviously to a processor, it can go through each of those little sections of code and therefore manage that and give us the impression that it's happening all at the same time. We can also use parallel processors. In other words, two independent processors running at the same time. Obviously, again, the advantages and sort of can come with this. You can have different types of processor then, and actually kind of control it. So if you wanted to, you could program for different situations, different usage types. More modern computers now have things like efficiency processors within there. They'll kind of again have performance processors, so they're considering what is needed for at the time. So it's becoming more sophisticated and flexible really in the need of the situation as it's presented. Within parallel systems, there are some advantages and disadvantages. You can see here we've got things like increased speed, but the disadvantages, obviously it's much more complex, and you need to then be able to synchronize activities, because one of the risks of this is that you don't actually use all of your capabilities within your computer. With parallel systems, what we've got is different types of ways of dealing with data. So we can have either multiple instructions and single data. We can have single instructions, multiple data. A simple example of that would be processing an image where each pixel within the image has just a binary number to represent its colour, and therefore all the processor needs to do is keep checking the colours and then displaying them on the screen. So by repeating that process, if you imagine like it could be thousands of pixels per image, you can just do all those all in one go very quickly. We can also have multiple instructions and again multiple data, so different scenarios can be coped with and therefore designed for. There are some problems, like I said, with multiple processors. If a parallel processor is sick, it needs to go to the doctors, because you can get things like deadlocks, you can get race conditions, you can get starvation, and it also has some synchronization issues. So a deadlock is when they effectively are waiting for each other. The race conditions are where it becomes down to the timing of the thread and what order it's executed. And then a process can also be starved. In other words, it just never gets dealt with, it never gets prioritized. And this can often come from synchronization, because if you imagine you're having to take and decide which of the threads is needing to be dealt with, and then some of those threads may rely on another thread being finished first, and therefore it can't be carried out, and therefore you get a delay in the processing speed. And again, like I said, just because there's more than one processor, it doesn't necessarily make it quicker. The programmer has to program for that. The clock speed will play an impact. The amount of RAM you've got will play an impact. So it's one of these things that we can't just assume that just by having more, like putting in more and more processors, that's going to fix the job. And it's one of the reasons why we have minimum user specifications, because the programmer has to think, well, what is the minimum requirement that I can expect of this computer? So it might be that they intentionally want it to run on a dual core processor, and therefore will have programming code that requires the two processors to actually carry out the various actions. Okay, well, I just wanted to say thank you for watching. I really hope you found it useful, and really hope you've learned something. Please do like and subscribe, and I'll hopefully see you again. Thanks a lot. Bye.